I'd like to take a look at ortho-para-directing groups and meta-directing groups and activating and deactivating groups. Over here on the left, I have ortho-para directing groups, and on the right we have meta directing groups. And if we just take a look at these, we notice some differences. All the ortho-para directing groups have an atom that is bonded to the benzene ring that can donate electron density by resonance or induction. And in the case of halogens, they can also donate electron density by resonance, although that's not the primary effect for halogens. They actually withdraw a little more electron density by induction. But over here, the meta-directing groups, the benzene ring is bonded to an atom that does not have electron density to donate to the ring. And so we can see that ortho-para directing groups have non-bonding electrons, or in the case of alkyl groups, they can donate electron density by induction. Meta-directing groups do not have that. These are also, at the top here, we have activating groups. And over here on the right side, we have deactivating groups. So the deactivating groups all withdraw electron density from the ring. Halogens are sort of in a special category. They withdraw a little bit of electron density from the ring, so they're weakly deactivating, but they're still ortho-para directors. So I'd like to take a look at why something like phenol is an activating group, and it's a strongly activating group. So if we just look at the resonance structures, we can actually tell a lot about why phenol is an activating group. And so the oxygen can actually donate electron density to the ring, so now we've got a negatively charged carbon here. Now this is this is a resonance structure, but this sort of illustrates how we've got a higher electron density in the ring, and so this is going to be more reactive toward an electrophile. So if we put an electrophile out here, these electrons will react with the electrophile. Now, the meta-directing, strongly, moderate, and strongly deactivating groups all have a similar function, and that is they withdraw electron density from the ring. And this goes for everything except for protonated amines. Protonated amines withdraw electron density from the ring because it's a formal positive charge. But let's just look at benzaldehyde as our example. We can draw a resonance structure where we put the negative charge on the oxygen atom, which leaves a positive charge on the ring. So this positive charge, so it's a partial positive charge that exists on the ring, makes these less reactive toward electrophiles. So when an electrophile is around, we have a positive plus a positive. This doesn't happen. So we don't have very fast reaction with electrophiles if I have a strongly deactivating group.